Welcome to a lesson with Dr. Powell. In this video, we will look in an abelian category and see why if we have a co-Cartesian square that looks like this with a fiber product of A and B relative to maps, that if the bottom map right here is an epi, then the top map will also be an epi. Duly, this will give us a result for a co-Cartesian square where we have the fiber coproduct of A and B. And if we have a monic right here between these objects, then we'll have a monic up here. Now, if we just simply apply the opposite functor to this diagram, we exactly get this one up here, except we'd have ops and everything. And so if we have the top implication, then we'll have these with ops, and just apply the reverse functor back from the opposite category, we'd get this down here. So really it suffices just to prove the top implication by duality. Okay, so let's get started. We're going to first show that if this C right here is isomorphic to the fiber product of A and B relative to these maps G and H, that C will actually be isomorphic to the kernel of a morphism alpha. And this morphism alpha will be defined via this diagram. Right here in the middle we have the direct product, direct sum of A and B, which are isomorphic to each other, inclusion maps, projection maps. And notice how we change this H to a negative H right here. Okay, so we're going to define, and so we can define alpha right here as in this, the morphism alpha as being the unique map such that we get some commutativity going on using the universal property of the direct sum of A plus B. So in particular, if we have IB then alpha, that's going to be the same thing as negative H, or IA then alpha, that's going to be the same thing as G. Okay, so that's how we can define alpha. We similarly can define beta using the universal property of the direct product of A and B. Okay, so now because of the universal property of the direct sum right here, and by uniqueness, we can actually say that alpha is going to be equal to the sum of a route going this way and a route going that way. We'll use that on the next slide here, particularly right up here. What we're going to do is we're going to show that C satisfies the universal property of the kernel. We're going to take an object, E, and a morphism, gamma, that goes to this direct sum, and then such that the composition gamma followed by alpha will be 0. So if that's the case, we can just replace alpha with the sum of these two routes going this way and that way, and compose it with gamma equaling 0, and distributing through, we actually notice that we get some things that are equal. In particular, if you go gamma this way or that way, we end up getting a actually, but notice we have just a positive H here because on this equality we moved it over to the other side. So actually we get a commutative diagram here, which looks like something we might want to see for C if we want to use the universal property of the fiber product itself. Going right here. Now notice, since we have this commutativity going on, there's a unique map sigma that makes all of this commute in here, which is kind of nice here. So we actually now have a candidate for this morphism sigma. So to satisfy the universal property of the kernel, what we need is, if we have a composition going to 0 here, that this composition will factor uniquely this way, so that beta of sigma will be equal to gamma, and then by that uniqueness, C will satisfy the universal property of the kernel of alpha. So the question kind of here is, we have this sigma already, but we need to show that actually beta of sigma is actually equal to gamma. So we have that beta is equal to IA of F plus IB of G, and that comes from uniqueness and the universal property of the direct product, using the fact that if you take beta defined in this way and then you follow it with PA right here, you will end up getting F from how PA acts against IA and I beta, or IB, that is. So with IB, it'll just zero out, and right here, that'll just become the identity right here on A. So we end up just getting the morphism F as desired for commutativity, for example, for instance. So by uniqueness, we do get that beta is equal to this, using the universal property of the direct product right here. Okay, so we can use that definition of beta, or that description of beta, here to show that beta of sigma is indeed going to be gamma. So if we precompose sigma to this, and then put it through the addition and take a look at this, so we have IA of F of sigma plus IB of G of sigma. Then we're going to use the fact that F of sigma is actually equal to PA of gamma right here. So in particular, that's because the way sigma was defined here using the universal property of the fiber product, where sigma came from, that's why we have these. That's why we have this. So F of sigma is going to be equal to so F of sigma is equal to PA of gamma, because in this diagram, that's where this map to A came from, is gamma, then running down. So you have that as well as you have this. So you can use these equalities here to replace F of sigma and G of sigma. And if you do that and then factor out the gamma right here, you get this map, which actually happens to be, notice that this is the sum of two things that start at this direct sum, come back like this, and by uniqueness, actually, this is the identity map, because the identity from this direct sum to itself, so if you start here, and you take your identity here, will be the same. You'll get the exact same thing here. You get the proper commutativity on this side as well as this side that you need. So therefore, it's going to be it's a unique guy that makes this work. It is going to be equal to the identity map, and so then you end up getting sigma as desired. So so the idea is, yes, we do get this equality, which means what? That the universal property of the kernel is satisfied. Therefore, C is not only isomorphic to the fiber product, but it's also isomorphic to the kernel of alpha, defined this way with a negative h. Recall how this negative h actually led to this commutativity right here via this little implication on the top. All right, so, but we actually get that these IDs are equivalent, and we'll use this, or at least a dual version of this. So if C is isomorphic to the kernel of alpha, then that'll actually imply that C is isomorphic to the fiber product. So we can work our way back that way by first assuming that C satisfies the universal property of the kernel of alpha, and then showing that C will satisfy the universal property of the fiber product. Okay, so so first of all, if we simply take an object E, and we have maps that go to B and A, such that we have so I have a map that goes this way, from B to A, such that we actually get commutativity. If this were happened to be a positive H, So if we did that, then that actually means that we're going to get, so if we did that, then we'll actually going to get that a certain map will be 0 when we put a negative h in here. Thinking of it as follows. So alpha, we can think of that as being the sum of two morphisms right here, or the difference of two morphisms with that negative h here. And here we can actually build a morphism from E to this direct sum, given commutativity, as we, given this W and R, using the universal, this W and R, and we're going to go to here using the universal property of the direct product and uniqueness. We actually, let's see, we can develop a map going on here. So we go this, we say this plus this going on, and maybe not uniqueness necessarily. I guess we just get a map. We get a map from E to this cross product, or no, I mean for this direct product, sorry, this direct product. So we get a morphism from E to this direct product, given a sum of this route plus this route. Now, okay, and then if you run through alpha right here, assuming that you actually have equality, that h of r, so that h of r, not negative h of r, but positive h of r is equal to j of w. We're going to make that, use that assumption. We're going to show that that indeed that okay, so that actually means that this composition will be 0, and I have it worked out here. You can take a look at that using this definition of alpha and making a morphism, and I call it T, that goes from E to there, just as the sum of those two routes, as I was explaining. So if you compose those two guys and work out and use the facts that if you intermingle the PA and IB or whatever, PB with IA, things zero out. So in this FOIL, you only really get like first and last. And using the fact that HR is equal to JW, then you'll end up getting 0. So you know that we actually have found a composition of two things that gives you 0, and using the universal property of the kernel, that implies that this map, so that actually implies that this map T will factor through the kernel. So we have that T right here factors through the kernel C, because we're assuming that C is the kernel right now, and we get a map sigma. We're going to show that map sigma, so there exists a unique sigma that makes this work from the universal property of the kernel, so it's unique already. We're going to show that sigma, though, actually makes this part of the diagram commute and this part, so that the universal property of the fiber product will be satisfied, in particular when this is a positive h right here. So it'll look something like this. So the question just amounts to make those commutativities work, is f of sigma equal to w, is g of sigma equal to r, and really just by definitions of how beta came about, f is equal to pa of beta, g is equal to p b of beta, the definition of how beta came about, and running those through, noticing that using from the universal property of the kernel, b of sigma is just equal to this, so you can input that in for b of sigma and run it through, and you'll notice, using the intermingling, zeroing out, but also pa of ia is actually, let's see, so pa of ia, so think ia and then pa, that's actually the identity map. That's how they're defined. I mean, they're defined using a universal property of direct product sum, kind of thinking about this part being identity anyway. So so that's identity, and also that's how you get zeroing out. That's actually from the definition, from how they can be defined, be each other with universal properties. You get identity, zeroing out, and so you get W, and similarly here for R. Okay, so, all right, so we've established something. We've established the equivalence of C being the fiber product or the kernel of such a thing, of an alpha if you make a negative right there. Great. All right. Well, actually, we could have, we made the H negative there, but we could have like made the G negative here and done everything with the negative G there. Why is that so? Because if you make both of these negative, think about in this Abelian category, like, additive inverse of additive inverse, like negative negative, it's going to become a positive. I mean, this commuting is equivalent to this commuting. So really, if you start here, you could go here, and then negating this map right here would look something like this. So, I mean, we get, and we're going to use that idea as well as we move along. So, all right, so we've established this equivalence right here. Now let's actually use the fact that this J is an epi. We haven't even come to that point yet, but now, J is an epi, all right. So, we're going to show first that this alpha will be an epi, okay? So let's take any object Q and a morphism that goes from D to Q such that when we follow alpha with M like that, we end up getting 0. So this being 0, and since we have commutativity right here, actually means that if we go, so that being 0 means that if we go this way, all right, so IA then alpha then M, we end up getting 0. And notice that IA alpha is actually equal to J, all right? But since J is an epi, that means that this M must be 0. So if this M is 0, so the implication that M alpha equaling 0 implies that M is 0 is equivalent to saying that alpha is an epi, which means that this sequence right here is exact. All right, now we should keep in mind that this exactness of the sequence still holds when alpha and beta are defined differently with a negative G and H instead of a G and a negative H. All right. So now, all right, since this is exact, if we apply the opposite functor, this will be exact right here, which implies that this guy is the kernel of beta op. So in the opposite category, if you just took the opposite of everything we were just working with, that actually shows you in this opposite category that since this is isomorphic to the kernel of this beta going backwards that way instead of the alpha, but it's all backwards, that you actually get that the op is isomorphic to the fiber product in the opposite category, which of course, but you also have to modify it because of, you see so that's where we were thinking of the H and G kind of swapping places, and that's for the opposite category idea that we were using, at least in terms of placements of things. And so that actually shows since we have this true in the opposite category for D, that means that in our original category that D will be isomorphic to the fiber coproduct of A and B, or the pushout. Okay, relative to the maps that we're working with, right? The maps, of course, with an FG and a positive H in that case, and J. All right, so we're going to actually use the universal property now. So to finish us off, to get this top guy being an epi, wow, all that work just to show that this guy down here satisfies the universal property of the fiber coproduct. All right, and that came about because this was a fiber product, and so this was a fiber product, and this right here happened to be an epi, and those two ideas together actually gave us that this guy right here was a fiber coproduct. So this square right now is co-Cartesian. All right, so we're going to show then that G is an epi. To show that G is an epi, we're going to take an object H and a morphism that comes to H from B, so such that when we take this morphism phi, and precompose it with G. So phi of G is equal to 0. That will imply that phi is 0. So to show that, all right, we're going to have the assumption that phi of G is 0. All right. And then what we can do is, why don't we just attach the zero morphism from A right there. Then we have a diagram that makes this whole thing commute with a 0 there and that map going to 0 there. And there is a unique morphism that goes from D to H, such that makes us all commute. And guess what? 0 works. So since 0 works right here, then, and we know that this composed with, so this 0 morphism precomposed with H right here is the 0 morphism. And since this is equal to phi, well, that shows us that phi is 0. Therefore, G is an epi. Okay, so we showed it. Thanks for watching.